There we go. Good. All right. Thank you very much. Pleasure to be here. I'm Colin Burke. I'm an NSF fellow at Yale, working mostly with Priya and Natarajan. I'm going to be talking to you today about some of my observational work, trying to look at local signatures of supermassive black hole seeding. So why do we care about black hole seeding? Well, we heard a lot on the Monday of the conference about high redshift supermassive black holes and overmassive black holes. And the consensus in the field is in order to form these supermassive black holes at high redshift, when the universe was only a few 100 million years old, you need to have some way of forming black hole seeds at high redshift that can then grow and accrete to become the supermassive black holes that we see today. And so I'm showing here, this is an excellent figure from MAR-MSQS 2017 review, showing redshift on the y-axis and black hole mass on the bottom. And this shows sort of the two more popular seeding scenarios or models. So the light seeds here on the left and heavy seeds on the right, which are about to form from direct collapse of primordial disks under specific conditions. And the basic idea is that, in the direct collapse scenario, you're not supposed to read all this. This is just to prove to you that this is an active area of research with many models and papers, of course. And so the idea is that for the direct collapse black holes, these should be rarer, so less common, but some fraction of them may be left over redshift 0 that we can observe, as observers can easily detect, right? And for the light seeds, those should be more common. So depending on the initial mass function of your seeds, modulo the degeneracies with mergers and their accretion histories, some population of low mass supermassive black holes between 10 to the 4, 10 to the 6 solar masses may trace what happened at high redshift. Okay, said that. So how do we measure the occupation fraction at low redshift, right? So the occupation fraction, just to reiterate, is the black hole occupation fraction here is what I'm talking about. So the fraction of local galaxies that have a supermassive black hole in their center, right? And so that could be sensitive to these relic populations at high redshift. So how do we measure this in local galaxies? Well, you just count them, right? You look with your X-ray telescope and you count the detections, but of course it's not that simple, not as easy as you would think. So just to demonstrate this, I've matched, very simply, just matched the Chandra source catalog here to this awesome catalog recently constructed by David Olson, which is galaxies mostly from Hyperleda and SDSS at less than 50 megaparsecs distance with a 1 arcsecond search radius. Okay, so I'm restricting only to galactic nuclei. And we see our detections here. So this is X-ray luminosity versus stellar mass. And you can see that we have inhomogeneous observations, so different exposure times with the Chandra observations. There's targeting biases. A lot of these are nearby well-known Seifert galaxies, for example, that were more likely to be targeted by Chandra proposals. And of course, lack of black hole estimates in these low luminosity galaxies, so we only have stellar mass for most of these. But we really want to use all the observations and all the data we can, especially in these low stellar mass regime here, which may be sensitive to the black hole seeding. So how do we do this? Well, we've constructed a statistical model. This is the only equation I'll show in the talk. So the probability of the distribution of the X-ray luminosities at a given stellar mass is given by a Bernoulli distribution, right? Which is equal to 1 if there's a black hole there, and equal to 0, so there's no luminosity there coming from the AGN, if there's no black hole, okay? This is multiplied by an active fraction. Not all black holes are active, which we assume to be not changing with mass in a significant way, which is consistent with some previous work in the X-ray. And then that's multiplied by your Eddington ratio distribution function, okay, which is a function of the black hole mass, but in this case we've used the stellar mass as a proxy involved with the Gaussian distribution to count for the black hole mass stellar mass relation, right? So that's why the scatter in this relation is huge, but nevertheless we can still use this as a counting model to infer our occupation fraction. And then we have to correct for X-ray binaries, which I'll talk about a bit later as well, which we think is actually a small correction since we've looked at the centers of all of these galaxies. Okay, and when you do that, you model your occupation fraction here as a function of stellar mass using some very unphysically motivated but flexible model called a Richards logistic curve. So this is just a smooth function between 0 and 1, and with some extra parameters that can be that define essentially the shape of this function, which is unknown, right? So in this case, the solid line here, this is where the occupation fraction would be 50% at 10 to the 9, rises to 100%, and then has a sigmoid shape, right? And it's allowed to vary. All these are free parameters in the model, okay? So what we want to constrain is the shape of this thing. And so as we go to increasing, or we change the this M50, so the shape, the position of this inflection point here is also allowed to be a free parameter. And we just tested to see whether our inferred likelihood is correct. So this is using mock data, the recovered point in the inflection point in the curve here on the y-axis versus the true inflection point in the occupation function here on the x-axis, and we can recover our, oops, sorry guys. Here we go. We can recover the occupation fraction pretty well until we get to this dashed line here, which is our selection limit that we've artificially imposed on the data. Okay, and below our selection limit, we can really only put a rough constraint or an upper limit really on the occupation fraction there. So, okay, so quickly we've estimated the contribution from X-ray binary contamination in our sample using the standard relation from Lemur 2010, which is based on the star formation rate of the host galaxies. Okay, so this is showing the X-ray binary luminosity that we would expect in our sources versus the observed X-ray luminosity. And so most of these sources are well above the X-ray luminosities that we would expect from X-ray binaries. This is the galaxy-wide X-ray luminosity, so we had to do a correction for the concentration index of the galaxy, assuming that the X-ray binary population roughly scales with the flux distribution, the profile, light profile of the galaxy, since we're only looking in a 1 arcsecond radius and centered on the center of these nearby galaxies, right? So this is okay, moving on. So in addition to the occupation fraction, we can constrain the X-ray luminosity function, the extremely low luminosity end of the X-ray luminosity function, just by convolving the black hole mass function with our inferred Eddington ratio distribution function, which in normal linear regression would be a log normal distribution, right? So this is a probability distribution function. In our case, this is a power law distribution of Eddington ratios involved with the Gaussian to get the uncertainties on our measurements. And so it appears, this is preliminary, but it appears to be consistent with an extrapolation of the nearby X-ray luminosity function from Topolo 2016. Okay, and this can be extended beyond, thank you. This can be extended beyond just X-ray data. And so I've been interested in looking at optical variability. So this is awesome work from Vivian Baldassare from a few years ago now, looking for these very convincing variable light curves from the Palomar transient factory light curves in very low mass galaxies. And so we've just plotted this time the change in luminosity from the RMS of the light curve, which correlates with the AGN luminosity, versus the stellar mass of the host galaxy here. And you can draw a linear regression between there with, again, a power law Eddington ratio distribution function, and go through essentially the same technique and get an occupation fraction constraint here. In this case, it's only a lower limit, but still a useful one. There's degeneracies in the optical variability case with the fraction of type 1 AGNs, which we can also fold into your model there. So that's the only additional term is the type 1 fraction for the optical variability, but it appears to be consistent. Reassuring. You can add the likelihoods together We've also done this, we're working on extending this to radio detections as well. And so this is quite preliminary, but if you add all of the likelihoods together, then you can create a joint constraint on the black hole occupation fraction, which is shown here, using all of the data. And that's shown in the gray contours here, 1 sigma and 95% confidence intervals outside of that. And excitingly, it appears to be consistent with the occupation fraction, very roughly estimated from detections of black holes from dynamical studies, dynamical black hole mass detections in local galaxies, and as well from the Trump 2015 paper, which did very careful forward modeling of the efficiency of detecting AGNs in SDSS galaxies, SDSS spectra, using the BPT diagram, so optical line ratios here, which becomes less efficient as you get to lower masses, but so that requires some sophisticated and independent modeling, but it's reassuring that our preliminary results are consistent with that. And the nuclei, you might be wondering, the nuclei curves here are just using the nuclear star cluster occupation fraction as a proxy for the black hole occupation fraction, right? So the fact that we're below there could indicate that not every nuclear star cluster hosts a black hole, or at least not one that we're okay. And we've shown here in the red points here the predictions from semi-analytic models from Ricarte and Natarajan 2018 for the light and heavy speed. So these are, these semi-analytic model measurements don't have any uncertainties though. Oh, and let me just say I'm going to skip through this, but we can also constrain the black hole mass function, which is consistent with the constraints from tidal disruption events by convolving our occupation fraction with the galaxy stellar mass function. And I'll skip over this. And so because these semi-analytic models have all of these uncertainties, which are difficult and degeneracies in the SAMs, what we're working on now is using an extension of the dark sage semi-analytic model, which we call dark sage black hole. And we've added a really simple, the simplest thing I could think of, power law seeding prescription to dark sage. And we're going to treat this power law index and the power law, the probability that every halo is seeded as a free parameter, in addition to the other free parameters in dark sage. In this case, there aren't many. And we're using the simulation-based inference techniques, which can learn the likelihood function in the semi-analytic models using a neural density estimator, essentially a normalizing flow, where you define your posterior or your prior distributions, rather, on these quantities, and then it learns the likelihood function directly. You can compare that to observed distributions of local black holes, their black hole mass, stellar mass, AGN luminosity, and instead of just calibrating with the mass functions, getting the mass functions and calibrating there, we can treat these quantities as distributions and match the covariances in the observations, which encodes information about the black hole mass stellar mass relation and the Eddington ratio distribution function self-consistently, and it's fully Bayesian. So this is still very much a work in progress in future work. Okay, I'm going to skip this and just quickly advertise. We have a Tinsley workshop in honor of Beatrice Tinsley happening at Yale. So this will be on high redshift galaxies and black holes with an emphasis on the JWST results, and the registration will open soon. So feel free to talk to me afterwards if you're interested or have any questions. I'm sure it'll be of interest to many. Yeah, thank you.
Thanks, Colin. Okay, so we have time for one question. Okay. Yeah. Thanks for the great work, Colin. This is Hao Zhang from the University of Arizona. And could you go back to the slide where you introduced the formula to estimate the occupation fraction? Yeah, right there.
Yeah, sure.
Okay, so I'm still a bit confused about the active fraction here. So where exactly does the information about active fraction come in? Like, that is not degenerate with your occupation fraction? Is it from like the X-ray AGN fractions that you observe at the higher mass range, or
Yeah, great question. I think it depends how you define it. So I think there are model dependencies here. The powerful thing about this technique is, we've defined the functional forms of all our parameters, and then you can then go and see what happens when you tweak them. But in our case, the active fraction that I'm showing here, I assume that it's independent of mass. So in that case, it breaks the degeneracy between that and the occupation fraction very smoothly with mass. But you can play around with that, and I'm sure there would be, you could map out those degeneracies there. I don't know what that would look like.
Could the next speaker please come forward? Okay, do we have one quick question perhaps? Because we're waiting for the next speaker. Okay.
Yeah, thanks for the talk. Marc Huertas Company from the ISC. On your SBI framework, you mentioned you're doing amortized posterior estimation, but then you mentioned that you're estimating the likelihood. So which one are you doing? It wasn't clear for me.
Well, maybe we should talk. So I'm still learning about the simulation-based inference, but my understanding was you define your priors, right, which are the free parameters in the SAM, and then the amortized posterior is basically technically it's learning the posterior, right? If you use uniform priors, then that's equivalent to learning the likelihood, I think, roughly. So, yeah. And then after that, you conditionalize it on observations.
Okay, thanks, Colin.
Thank you.